Hello, my name is Oran Berry, and this poster is about two works that we did to understand and design antiferroelectrics from atomistic simulations. Both works have been carried out under supervision of Jorge Iñiguez at the Luxembourg Institute of Science and Technology. Now on the left we can see a recent work that we published this year, and this is the reference. We propose ferroelectric paraelectric superlattices as artificial antiferroelectrics for energy storage applications. Okay, so when you sandwich a ferroelectric between paraelectric layers, a competition arises between the polar distortion and the electrostatic energy. Now, this competition often results in the ferroelectric breaking into domains with opposite polarization. The resulting state can be considered antipolar and has been observed in many systems, including lead titanate strontium titanate superlattices, which are getting increasing attention over the last years. Now, when you apply an electric field along the direction of the polarization, these superlattices can fully switch into a polar state. So we have an antipolar system that can switch to a polar state when subject to field, and hence we have antiferroelectric-like behavior. So one advantage that these artificial antiferroelectrics pose is that there are several design parameters that we can use to tune their response, like the thickness of the ferroelectric or the paraelectric layers or the epitaxial strain. So we use second principles atomistic models of lead titanate strontium titanate superlattices to compute the response of these superlattices under field, and we did so for more than 1000 sets of design parameters, paying special attention to their performance for energy storage, that is, how much energy they can store as capacitors. Now the results of these high throughput calculations are summarized in these parallel coordinates plots, which are very helpful to visualize correlations in large datasets. So with this data, we can optimize the response for a given applied field, and we find that the performance is always optimal for applied fields just above the switching field. Now for large fields of 3.5 megavolts per centimeter, these superlattices can store more than 100 joules per centimeter cube, a value that is only surpassed by a complex perovskite solution that holds the present record. Okay, so to sum up this part, we propose ferroelectric paraelectric superlattices as artificial antiferroelectrics for energy storage, and we find that these systems can be optimized precisely for energy storage applications. So we study in particular lead titanate strontium titanate superlattices, finding that the results are competitive with state-of-the-art. Okay, so now let's move on to the other work. Now on the left, you can see a second work that we have published last year under this reference here. And here we study the well-known antiferroelectric perovskite lead zirconate. So we found several hints in the literature pointing at uncompensated dipoles in lead zirconate, and therefore we decided to study or to build a ferroelectric phase for this compound. So for this ferroelectric phase, we imposed a dipole pattern of dipoles going up, up, down, instead of the usual up, up, down, down of the antiferroelectric phase. Now on that structure, on this ferroelectric dipole pattern, we superimposed the octahedra tilt pattern of the ground state and took the resulting structure to our favorite first principles code and optimized it. So to our surprise, we found that this phase shows a lower energy than the usual antiferroelectric phase. So we decided to then compute the free energies as a function of temperature using the so-called harmonic approximation. Now we included two more phases in the mix as a sanity check. So we found that the ferroelectric phase is the most stable phase up to somewhere between 250 and 460 Kelvin, when the usual antiferroelectric phase takes over and becomes the most stable phase. We checked our results against the choice of exchange correlation functional, and we also computed the effect of the thermal expansion using the so-called quasi-harmonic approximation, finding that our results are robust. So we discuss how our results can be reconciled with the experimental knowledge we have already of lead zirconate, and most importantly, we find that our results indicate that the ground state of lead zirconate may not be antiferroelectric, but rather ferroelectric instead. So thank you for listening, and come by my poster or contact me for further details and discussion. Thank you.